So, today we will discuss a representation for integers based on some residues. So, let us suppose we have two integers x and y. Well, we will only be dealing with non-negative integers. Then we say x is congruent to y modulo some other integer p if and only if p divides x minus y. Now, therefore, x minus p, x minus 2p, similarly x plus 2p and so on, x plus p rather, x plus 2p etc. are all congruent to each other modulo p. Hence, there is always an integer in the range 0 to p minus 1, which is congruent to any given integer x. So, in today's discussion, we will denote such integer as x mod p. So, this is an abuse of notation, and this denotes that integer which is congruent to x and is in this range 0 to p minus 1. For example, if p is 10, then 27 mod p, that is 10, is 7. So, this is our notation. Now, today we will describe a representation for integers using these numbers which are residue modulo p. So, let us suppose we have some n integers p0, p1 through pn minus 1 mutually co-prime that is pick any two of these integers and their GCD is 1 given such. So, I should just say given and given any integer u, we will define u mod pi as ui. So, if I compute the residue with respect to each pi for this integer u as ui, then Ru, which I am defining as a tuple, is u0, u1, un minus 1. So, for any integer u, we define this tuple which is the residue of u with respect to each of these integers p. So, we describe a useful theorem called Chinese remainder theorem. Which says let p be the product of pi 0 to n minus 1, then there exists a 1-to-1 correspondence between the set of integers and the tuples Ru such that U belongs to the corresponding set in other words, for every integer in the range 0 to p minus 1, there is a unique n tuple Ru which is given by the residues of that integer with respect to the n integers p1, p0 through pn minus 1. To prove this, well, it is obvious that for any integer there is a unique tuple because there is a unique residue with respect to each pi. Okay. Now, let us try to prove the converse. Suppose U1 and U2 are in the range 0 through p minus 1 such that R of U1 is same as R of U2. In this case, we want to show that U1 is actually equal to U2. So, let us say that we have, okay, let us use some other integers U and V, U and V, and we want to show and assume that Ru is equal to Rv. We want to show that U is equal to V. So, what we have is U1 rather U0 through Un minus 1 is equal to V0 through Vn minus 1 because of the fact that the two tuples are equal. That is, Ui is Vi for all I, or Ui which is U modulo Pi is equal to Vi which is V modulo Pi. Hence, so Pi divides U minus Ui which is equal to U minus Vi. Pi also divides V minus Vi. Hence, Pi must divide the difference of the two, which is U minus V. Okay, this is true for every I. Since Pi's are co-prime, the product of Pi's 0 to n minus 1 also divides U minus V, which is same as P divides U minus V. But by our choice, both U and V are in the range 0 to P minus 1, since U and V both belong to the range 0 through P minus 1, U must be equal to V, that is U minus V should be 0, which establishes the one-to-one correspondence between these tuples and these integers. So, in some sense these tuples represent these integers, and in certain computations this representation can be very handy. Two binary operations, namely addition and multiplication, can be done in this representation as follows. So, let us suppose we have U and V in the range 0 through P minus 1, then u plus v modulo p, which is the representation of the sum of these two, or the number corresponding to u plus v in this range. This is equal to u0 plus v0 modulo p0 un minus 1 plus vn minus 1 modulo pn minus 1. What we have here is that the representation of u was u naught, u1, u2, u3, un minus 1, and that of v was v naught, v through v3 through vn minus 1. Then all you do is you take the corresponding components, add them up and compute the modulo with respect to the corresponding pi, and you get the representation of this number. And the similar claim is true for multiplication. Vn minus 1 modulo p n minus 1. Okay, to see this, let us just take one in the first case, u plus v modulo p has a representation, namely u plus v modulo p modulo p naught, and so on. This is how we will write the representation of u plus v modulo p, but this is equal to u plus v mod p naught and so on. The reason is that p is a multiple of p naught, is true. Now, let us take u naught, which is nothing but u mod p naught, and v naught is v mod p naught. So, u is some C1 p naught plus u0, v is C2 p naught plus v0. U plus v therefore is C1 plus C2 p naught plus u0 plus v0. Hence, u plus v modulo p0 is on this side. When you do modulo p0, this vanishes and you are left with u0 plus v0 mod p naught. And this is exactly what we are computing. This quantity is same as this, and therefore these two are equal. So, this is true for any pi, and similar argument holds for the multiplication. So, this is just telling us that you can perform these operations in the new representation. Now, let us talk about how to compute efficiently the new representation. So, let us come to the algorithmic aspect of this computation. First of all, let us define q 0 0 as p naught, q 0 1 as p 1, q 0 2 as p 2, q 0 3 as p 3, and so on. To be able to perform the computation we are going to do, we will assume that n is a power of 2. This goes on. So, if I multiply these two, that I am going to denote as q 1 0 as q 0 0 times q 0 1, q 1 2 as q 0 2 times q 0 3, and so on. Product of these will be called q 2 0 as q 1 0 times q 1 2. So, we define in general q j I as q j I into q j I plus 2 to the power j minus 1 I, q j minus 1 I into q j minus 1 I plus 2 power j minus 1. Okay. So, where j ranges from 0 through k, and the range for I will be, I will range from 0 to 2 power j, 2 times 2 power j, 3 times 2 power j, and so on. So, how do I compute this? Well, exactly the way we have stated. So, to compute the q's, we will say for I equal to 0 to n minus 1, q 0 I is p I, for k equal to 1 to n, do for I equal to 0 to n minus 2 power j in steps of 2 power j, which means 0, I equal to 0, I equal to 2 power j, I equal to 2 times 2 power j, 3 times 2 power j, and so on. The last being n minus 2 power j. Remember, 2 power j divides n. We write down the same relation, q j I equal to q j minus 1 I times q j minus 1 I plus 2 power j minus 1. Okay. Now, that size of each p I is at most b, and as q j I is same as p I into p I plus 1 all the way up to p I plus 2 power j minus 1. So, the size of q j I is at most 2 power j times b. This operation takes m 2 power j minus 1 times b, which indicates multiplication of two integers of size 2 power j minus 1 times b, that is the size of these two integers. The time it takes to complete this loop is 2 power n by 2 power j into m 2 power j minus 1 times b. That, because of the fact that m is worse than linear, can be bounded by n by 2 into, rather 1 by 2 into n by 2 power j minus 1, my mistake, we will say 1 by 2 m n by 2 power j minus 1 into 2 power j minus 1 into b, which is equal to 1/2 m n b. Finally, this loop, which runs k times, so the total complexity is of the order of k times m n b, which is same as order m n b into log of n, which is k. Now, let us try to compute the modular representation of any integer u in the range 0 through p minus 1. So, let us write down the algo. The input is u in the range 0 through p minus 1, and output is supposed to be R u, the tuple residual residues with respect to each of the n integers. So, this time we proceed from in the opposite direction. Let us define u, let us separately first define it here. Let us define u j I to be u modulo q j I. Okay. So, what is its relationship with u j minus 1 i's? So, let us take a look at u j minus 1 I. U j minus 1 from the definition is u mod q j minus 1 I, which is same as u modulo q . Let us observe that modulo, before I can expand this, modulo or rather any number x modulo y is equal to x modulo y times z, and the whole thing modulo y. That is to say, if we compute the remainder of x with respect to the division by y times z, and then take that remainder and again divide by y, you will get the same result as that of by directly divided by y. Now, if that is the case, then we can use the following result. We can compute first of all u modulo j minus 1 I into q j minus 1 I plus 2 power j minus 1, and then we compute modulo qj minus 1I. Okay. There, this number is u modulo q j comma I, and then we compute modulo q j minus 1 I. So, if we already have computed u j I, then we can replace this expression by that value and compute modulo q j minus 1 I. Similarly, we can show that u j minus 1 I plus 2 power j minus 1 is also equal to u j I, but this time we compute modulo q j minus 1 I plus 2 power j minus 1. We will use these expressions to descend from u k 0 down to u 0 of various values. So, we will begin with u k naught as u, then for j going from k down to 1, and for I from 0 to n minus 2 power j, rather in steps of 2 power j, in steps of 2 power j, do. And let us compute u j minus 1 I as u j I modulo q j minus 1 I and u j minus 1 I plus 2 power j minus 1 similarly is u j I mod q j minus 1 I plus 2 power j minus 1. So, this way finally we will get u 0 i's. What is u 0 I? U 0 I by our definition is u modulo q 0 I, which is same as u modulo p I, that we are calling u I. So, that is these are the components of the representation. So, we denote the u 0 i's as u I for I equal to 0 to n n minus 1 u I is u 0 I. So, return u 0 through u n minus 1. Well, the time complexity of this process, once again recall that these numbers have size at most, let me just write this down, is 2 power j minus 1 times b. Okay. 2 power j minus 1 times b, therefore, these numbers cannot have size more than 2 power j minus 1 times b. This is 2 power j times b at most, and you are dividing it by 2 power j minus 1 b. So, this modulo computation is a division of 2 power j size number, 2 power j times b size number by 2 power j minus 1 times b number, which from our earlier lectures we have seen has same complexity as a multiplication of 2 power j minus 1 b size numbers. So, both of these involve this much computation, and the inner loop, the inner for loop runs n by 2 power j times. So, we have n by 2 power j into 2 times m 2 power j minus 1 b time bound, that again because of worse than linear time complexity of multiplication has to be n by 2 power j minus 1 into 2 power j minus 1 b, that is m n times b. Once again the outer loop runs k times. So, the time complexity of this will be k. So, the total time complexity is a times m n b, which is same as order m n b log of n, which is the same time complexity it takes to compute all the q j i's. Hence, the entire process, computation of q's as well as the representation of u, takes this time. Now, let us compare the same computation if it is done in a direct fashion, that is, if we compute each ui, let us say ui directly by computing u modulo pi, then how much time it takes? Let us use a notation c of x comma y as the time to compute x modulo y. For us, u is a number in the range from 0 to p minus 1. Size of p can be at most the size of p, note that it is p 0 times p 1 times p 2 up to p n minus 1. So, this is of the size n times b. So, this process will take c of, if I write down the sizes of the two numbers, we are computing the modulo of a number of size n times b. We are dividing this number by a number of size b. Okay. So, maybe I should say the sizes. This is a number in the range 0 to p minus 1, hence in the worst case it could be of size n times b. Now, if you are dividing a number by of size n b by a number by b, so it is a reasonable approximation that this is going to take about n b by b c b comma b. Because you have to divide an n times a larger number in size compared to the number the divisor. So, this is about n c b comma b. B comma b can be approximated as m b. So, we are taking this much time to compute one component. So, the entire representation, the time for the entire representation will be, well, approximately n square mb. Now, to compare with our algorithm's time, let us suppose m of x is x power 1 plus alpha. We know that it is worse than linear. So, let us say it is about x to the power 1 plus alpha. Then this thing turns out to be n square times b to the power 1 plus alpha. As compared to that, the time we have taken in the algorithm is log of n times m of nb, which is log of n times nb power 1 plus alpha. So, if you take the ratio, the speed up will be n square times b power 1 plus alpha divided by log of n times nb power 1 plus alpha, which is n to the power 1 minus alpha divided by log n. So, it shows that there is a significant improvement as long as alpha is relatively smaller than 1, which we know it is. So, now let us try and look at the problem of reverse computation. So, question is how to compute u from RU. So far we have been showing how to go from u to RU, but how to go backwards. So, for that again there is a nice result which allows you to compute u from RU. First of all, let us try and define a few things. Let us define Ci as P divided by Pi. Okay. Now, we make a claim that for each I there exists a di in the range belonging to the range 0 to pi minus 1, such that Ci into di is one congruent modulo pi. In other words, di is a reciprocal of Ci modulo pi. So, to show this, let us observe that Ci, which is a product of P0 through Pi minus 1, Pi plus 1 all the way to Pn minus 1. So, this is co-prime with respect to Pi, because each of these is co-prime. Okay. So, GCD of Ci and Pi is 1. So, there exists alpha and beta such that they could be positive or negative, such that alpha Ci plus beta Pi is 1. If you take modulo P of this equation on both sides, what you get is alpha Ci is 1 mod Pi, because this vanishes when you compute the residue. with respect to pi. Hence, alpha is the number that we are looking for, but observe that if alpha does this, then alpha plus any t times pi into ci is also 1 mod pi. Hence, any number here can work as long as it is congruent to alpha with respect to pi. Hence, there exists an alpha in the range 0 to pi minus 1 such that alpha times ci is 1 mod pi. So, this establishes the existence of this alpha is our di. Then we have the following theorem. Let Ru be u0 through u n minus 1 di be such that ci into di is 1 mod pi for all I. Suppose we are given these, then u mod pi, the residue of u, or if we assume that u mod p, not pi, mod p. If we assume that u is already in the range 0 to p minus 1, then this is same as u is equal to ui ci di mod p. And to show the correctness of this claim, which is very easy, let us take the modulo pi on both sides. So, u mod p mod pi, which is the left hand side now. Note that pi is a factor in p, so this is same as u mod pi. Okay. So, the left hand side is nothing but ui. Well, which is correct, because after all this is what we expect when we compute the modulo pi on the left hand side. If this is indeed equal to this, then we should also find that the modulo pi of this sum is ui. For the right hand side, if I take the sum I equal to 0 to n minus 1 ui di ci mod p mod pi, once again this is same as sum 0 to n minus 1 mod pi. Note that I should change my index. Let us use some other index, call it j, because this is a dummy index. And we are computing modulo pi. Every Cj is divisible by pi except Ci. That is how we have defined our note that Ci is all the product of all the p's other than pi, hence it is divisible by every pj's other than pi. So, Cj mod pi is 0 for all j other than j equal to I. So, this reduces to ui di ci mod pi. Other terms have vanished. Hence, this can be written as ui times di ci mod pi whole thing modulo pi. But this is 1. So, this is nothing but ui into 1 mod pi, but that is equal to ui. So, indeed this number has the same residue with respect to pi as u. So, from the uniqueness we know that this and this number are same modulo p. Now, finally, let us go ahead and compute the integer u from the components ui's. So, now to compute u from the residues, let us define as ji sum p I into p I plus 1 all the way to p I plus 2 power j minus 1 divided by m into Cn into dm, where m starts from I and goes up to I plus 2 power j minus 1. If we define it this way, then S k 0 is precisely u, provided we compute. So, let us assume that we do modulo p. S k 0 modulo p is u. The values of S 0 i's are precisely C I into d I. So, let us see the relationship, how the recurrence relation can be set on this. Let us define, let us we have this S j I as defined here. We can now split this in the following way, that S j minus 1 I into q j minus 1 I plus 2 power j minus 1. Note that if m is less than I plus 2 power j minus 1, that is to say it is in this half, m is in this half, then this whole thing will be nothing but q j minus 1 I plus 2 power j minus 1. So, we can take that factor out from all those sums where m is in the lower half, and for higher half we can take the terms out of this in the similar fashion, and that is what it gives you. So, we get S j minus 1 I plus 2 power j minus 1 times q j minus 1 I. Okay. So, this allows us to actually compute the value of S for higher values of j. So, once again we will set up a program starting with the lower level for I equal to 0 to n minus 1 S 0 I is C I into d I. We assume that d i's have been pre-computed. For j, equal to 1 to k do for I equal to 0 to n minus 2 power j in steps of 2 power j do S j I S j minus 1 I q j minus 1 I plus 2 power j minus 1 plus S j minus 1 I plus 2 power j minus 1 times q j minus 1 I. And u is nothing but S k 0 mod p and return u. The sizes, note that we can, instead of using the CIs as it is, we can replace them in the range their modulo. So, we can replace them by Ci mod Pi. We can replace, we already have decided to use a number here in the range 0 to Pi minus 1. So, the sizes of, let us take a look at this Sji here. Sji has the size, individual term here has got 2 power j into b bits in the numerator. These also have at most b bits minus b bit. So, each of these is 2 power j b plus b bit size at most. This is the maximum an individual term can have, and we are adding up 2 power j such terms. So, adding 2 terms adds the size by 1 bit. So, the total size of Sji is at most 2 power j b plus j. After adding up 2 power j terms, this is the maximum number of bits you can have, which we can comfortably assume to be plus 1 times b. This is the maximum size. So, this computation involves multiplying a 2 power j plus 1 b bit number with a 2 power j times b bit number with a 2 power j minus 1 size b times b bit number. So, let us suppose this involves 2 times m 2 power j into b multiplications. Hence, this will take n by 2 power j into 2 times m 2 power j times b, which is in our usual argument we have shown that this is at most 2 times m n times b bits, and this is k times 2 times m n b. Once again, the time complexity of this is m n b into log of n, which is k. Once again, it is the same time complexity it takes. So, this is all we have. It takes the same amount of time to go back and forth between the number and its residual representation. In the next class, we will show that the same ideas apply to polynomials.